Hey guys, welcome. Yeah, so first and foremost, as always, thank you, Lord Jesus Christ, for everything. And second is I have a super exciting video for you here because I've been wanting to make a video on this topic for a while, but usually, I have to be into the topic because, you have to figure out how to deliver it well, blah, blah, blah. And so I'm in the mood for it now, and so let's do it. All right. So the question we're trying to answer is, when is a function integrable? In other words, given a function, when can we say, all right, this is just like a crazy function, we can't find the integral of it? I'm going to give you an example, but we're going to first talk about the big picture, okay? All right, this is not quite the Riemann sum definition of integration, as you'll see, but we have the notion of a lower sum and an upper sum, as you'll see in a second. And of course, as I've said in the past, my favorite calculus book, which is really an analysis book, is simply called Calculus by Michael Spivak, and so he does a very similar argument there in that book, so credit where it's due. But yeah, this is super fun. Yeah, okay. So another way to state this question is, when is a function not integrable? Right? Okay, enough said. So first, terminology. We need to really understand what these two words mean. So one of them is infimum. And we will abbreviate for infimum with just I and F. And the next one is supremum. And we will abbreviate for supremum with sup. So given a set A, let's say the set A is the interval from 1 to 2, right? That's infinitely many numbers, but given that set, inf A, right? I'll write it here. Inf A would be equal to 1, and then sup A would be equal to 2. So given a set of numbers, the infimum is the the infimum is the greatest lower bound. So notice for this set, 0 is a lower bound, -1 is a lower bound, and so is 0.999. 0.999 is a lower bound because nothing in this set is smaller than 0.999. But of all the lower bounds, notice there are infinitely many lower bounds. The biggest of them, that is infimum A. So infimum A is 1 because, of all the lower bounds, the biggest is 1. Yeah? And similarly, supremum is the least upper bound. So, an upper bound for this set is 3, 4, 5. Anything bigger than 2 is an upper bound for this set. But of all of the upper bounds, the smallest one is 2 for this set anyway. And so we'd say that sup A for this set A is equal to 2. So these two guys will play a prominent role. So in the play that's to come, they're the stars of the play. Yeah, okay. All right, the mathematical play, of course. All right. So after this, what should we talk about? Well, we should talk about a partition P. So a partition P of the interval AB. So a partition of the interval AB. Oh, sorry, I wrote AP. I'm eager to yeah, you get it. So partition, let's call it P, the partition. So a partition P of AB would be basically breaking AB into a bunch of connected line segments. That's basically, the endpoints of those broken line segments are the partition. So I'll state it and you'll see what I mean. So a partition of AB would look like this. So say A is equal to T sub 0, then we'll have T sub 1, T sub 2, and on all the way to T sub n minus 1, and then finally T sub n, where obviously T sub n is B. So this is a partition of the interval AB, or a partition of AB. And so notice then that we'll have intervals going from T0 to T1 and then T1 to T2 and yada yada. Unlike the Riemann sum, these intervals don't have to be equal. So if we take T sub I minus 1 and T sub I, right? Then this does not need to necessarily equal to T sub I and then comma T sub I plus 1. In other words, the partitions these don't form intervals that are necessarily equal. We don't need that. But remember, in the Riemann sum definition of the integral, that was a very useful assumption so that we could factor out the delta x. But that discussion I already have in a different video, the Riemann sum definition of the integral. So I'm not going to mention it enough here because, well, let's focus on the task at hand. So you get what I mean by a partition. Obviously, if I have n growing, then we're breaking up a v when we're writing intervals into smaller and smaller pieces. And in fact, you will see what we're going to do in the end is really think about what happens when n goes to infinity, right? So that's akin to the Riemann sum definition of the integral. But anyway, you just need to understand what a partition is. Partition of AB, we've got that. And so now let's talk about these very important items. Okay, so let's define, and let me do it over here. I can do it over here. Let's define, and I can do it in black, m sub I, little m sub I, to be equal to the infimum of let's see, f of x on t sub I minus 1 is less or equal to x is less or equal to t sub I. Wait, what? What am I talking about? Well, little mi for any one of these intervals, so between t1 and t2 or t2 and t3, any two consecutive t's, right? Between any of them, what m sub I is it's the smallest y value achieved by f on that interval. Now, keep in mind that when we do Riemann sums, if our function is increasing, the smallest y values on the left, we call that a left Riemann, and then our biggest y values on the right, if the function again is increasing, right? And this is not like that. It allows for like the function to dip in a given interval, and therefore the infimum would be like there in the middle, or wherever it dips, wherever the function achieves its lowest value. So important is this little mi, well, obviously corresponding to this ti, and therefore in this interval, this little mi is the smallest y value attained by f on this interval. So like, let's make it more specific. So little m2 would be like inf, right? This is so crucial to your understanding of this video that like we should probably like break it down some more. So little m2 would be the infimum of f of x on the interval, so t sub 2 minus 1, so t sub 1, and then t sub 2. So little m2 is the smallest y value attained by f of x on the interval t1 to t2. Yeah? Okay, cool. But I need the space actually to define capital M sub I, so we're done with the example. So capital M sub I then is equal to, take a wild guess, it's going to be the supremum of f of x on t sub I minus 1 less or equal to x is less or equal to t sub I. So on the same, and this should not be like a square bracket, but you're fine, you live, right? So it should be like ending the, yeah, you get it. Okay. So we're saying that on the same interval, like looking at the same interval, capital M sub I is the highest y value attained by f on that same interval. Yeah? Okay, cool. So let's get some visuals going because that'll help you understand this some more. Yeah? Okay, cool. Let's do that. So here it goes. This is cool. So like we're saying like, like if your function, let's say, is a decreasing function, so let's take a function that's like, that looks like this, right? And let's say this is the x-axis, right? And the y-axis, obviously this, right? Okay. And we take some like t sub I minus 1 here, and then some t sub I. So we've like zoomed in on the function, because remember, if we have a lot of t's, then this is a very small interval. Anyway, we look in here, right? And that will be useful for some of you. And so we see that little m sub I is going to be this, right? Little m sub I is going to be this. And then big M sub I is going to be this, right? Capital M sub I is going to be that. Okay, fine. So you get it. And obviously, well, not quite maybe, like, but here's some reinforcement on the way. So like, obviously, if the function is increasing instead, right? And again, we take some interval t sub I minus 1 and then t sub I, right? Now capital M sub I is going to be on the right side, obviously, because it's the highest y value attained for the function f, this, and this interval, and that's clearly right there. And then this is, so capital M sub I, and then this here is little m sub I, right? Okay, but I want to make clear what I said earlier, which is that, like, it's not like left Riemann and right Riemann, because, well, capital M sub I or little m sub I may be somewhere else other than the endpoints. I'll give you an example. So suppose that when we zoom in on the interval t sub I minus 1 to t sub I, our function does this, which is that, like, our function does this, which is that, like, it dips like that, right? And suppose that our interval for t sub I minus 1 to t sub I goes here, right? Okay, then now capital M sub I is going to be, like, I've made it somewhat symmetric, but it looks like the highest y value will be somewhere over here. So I guess let's not make it so symmetric. Well, obviously, if they're equal, capital M sub I would be either of those two. But let's make them, like, you know, distinct that way, like the, you know, the symmetry that I had going. I needed to break that. Anyway, capital M sub I is where I have it, right? And it's the highest y value attained by f. On the interval here, and little m sub I now is no longer right there. Little m sub I is right here, right? So and that's little m sub I, my bad. So little m sub I is right there, so it corresponds to some t value between these two guys, right? Okay, all right, but the point is that, like, now what we want to do is look at this. So what does this define? Like, on this interval anyway, this defines a single rectangle, but a rectangular approximation of the area under the curve, and this interval anyway. Now, what is that? This smallest rectangle. Now, because of the way we defined little m sub I, the rectangles where little m sub i's are used as a height are going to be the smallest possible rectangle in each interval, right? And so I'm saying, like, you know, if we use left Riemann right now, it would not be the smallest rectangular approximation of the area, because it'd be like a taller height for the rectangle, right? So the little m sub i's, they're going to help us define the smallest possible rectangle as an approximation of the area on any interval t sub I minus 1 to t sub I. And guess what? Capital M sub I is going to give us the largest rectangular approximation. Now, let's find the area of this rectangle, right? The area of this rectangle is little m sub I, and then times what? Times t sub I minus t sub I minus 1. And then correspondingly, the biggest rectangle that we could find in here, right, is going to be this rectangle, right? Like, and that will have area, it will have area capital M sub I times t sub I minus t sub I minus 1, right? Okay, cool. But then wait, if we broke the interval from a to b into these bunch of t's, then to find the smallest rectangular area approximation for the function f on the entire interval from a to b, what we have to do is the smallest rectangular approximation of the area, this arrow no longer, like, applies, is going to be the sum of these guys, right? So in each interval we find the little m sub i's that will give us the smallest possible area in that interval, right? And then we multiply by the length of the interval and add up from I equals 1 to n, right? And so that means that we involve t0, that's our a, and we involve tn when we get there. T sub 0 is when I is equal to 1, and t sub n is going to get involved when I is equal to n, right? Anyway, this is a good definition for an area approximation of the region under the curve, the area under the curve. Sorry. Like, I'm, like, so passionately going on this that, like, I'm, like, kind of like forgetting to take a moment of, like, whatever it is, like a deep breath in. Okay. But I'm saying that this here is the smallest rectangular area approximation of the area under the curve. I hope that made sense. And we're going to give it a specific name. And we're going to call it the lower approximation of the function f with partition p. So remember, we haven't decided how many pieces we're going to break the interval into. So obviously, there are different p's. So in this definition, we can vary p is what I'm saying. So we can change n, and so that will, like, you know, change the number of t's we're using, and therefore that in turn changes the partition, right? So we will consider all partitions in a second. But this right now is a good definition of what we mean by the smallest rectangular approximation of the area under the curve f, right? From A to B, obviously. And so then very similar ideas will say that this guy here up top should be called the upper rectangular approximation of f for the same partition P here, right? And so, like, didn't leave myself in F room, my bad. Upper, and then F, and then P. And obviously, the room was to write sigma here. Right? Sorry, sigma. That's so poor. My bad, guys. Okay, equals sigma. Okay, and obviously sigma goes from I equals 1 to n, right? I equals 1 to n. Okay, now, so when we change partitions, right? Like, what's gonna happen? Let's say that, like, we have one partition different from another partition. Then we can distinguish each partition as, like, L1. So yeah, so L1 is concerning partition 1, so whatever partition 1 may be, and L2 would be like partition 2. So like, you know, I don't need to write these L1s and L2s and LNs and so on. Like, we're saying, like, there are different partitions, and so you should get that for different partitions, the value of this is going to be different. In other words, there are different L of FPs. That is this L function, right? When we change the partition, it gives us different output. Obviously, when we increase the number of t's, that's when we use a larger n. The area is going to be, the approximation given here is going to be closer to the actual area, right? Okay, cool. And so what I'm saying is, it makes sense to talk about this. It makes sense to talk about soup, L of F P. That is, it makes sense to talk about the supremum of all of the areas given by L, right? I just said when you change the partitions, the areas change, right? Like, I'm changing the number of rectangles in essence. And so when I change that, L gives me different values. And so sup L is going to tell me the biggest of them. So the biggest lower rectangular approximations of the exact area under the curve. Okay, cool. And then similarly, we define infimum of UFP. And now remember, the U's, right, what they do is they find the biggest rectangular approximation of the area under the curve, right? Adding up, obviously, like, all of the little intervals, or all of the little rectangles over the little intervals. Anyway, notice that these guys, which are like bigger, because, well, they're bigger rectangular approximations, they too change depending on how many partitions we have. Or that doesn't make sense. It doesn't make sense to say how many partitions we have, depending on what the partition looks like. The point is, though, we have different partitions, so when the partitions change, then the U's change, and therefore it makes sense to talk about the smallest of the U's. So when the largest of the U's is equal to the smallest of the U's, that's the exact area under the curve. So when sup L is equal to inf U, that will equal exactly the area under the curve A to B f of x dx. Because basically, when will that happen? When will sup L equal inf U? When we're using infinitely many rectangles, because then in that case, like, the intervals collapse to, like, basically a single point, right? And there, in that interval, like, the MIs, these two MIs will equal, and obviously the interval width is now dx, and so basically we get that this will be equal to this when the partition has infinitely many, like, t's in it, right? Okay, so cool. So when is a function not integrable? When this cannot be true. When sup L cannot equal inf U. Wait, that's possible? Yes. Some functions behave so badly that sup L cannot equal inf U. And so I'll give you an example. That's what this was sitting there for. And so, like, you know, but, like, I thought this was really, really cool. Well, the math, not like, okay. And so I hope you agree. But even if you disagree, whatever, like, you're not cool, and I don't care. But yeah, like, let's do this. So let's give you the example that I spoke of. So consider this function, which is a very bad behaving function. So it's a crazy function. So the function is f of x is equal to, and then let's say 0 if x is irrational. X is irrational. Crazy. And then it's 1 if x is irrational. If x is rational. Right? Ooh, cool. What would this look like? Well, if the interval a to b is like a is here and then b is here, obviously from our earlier talk, what a is really it's t sub 0, right? And then b is really t sub n. This doesn't have too much consequence for what's going to happen to this. Well, the naming, it's just naming. But what does this function look like? Now, remember, by the density of the rationals and the density of the irrationals, if we take any interval t sub I minus 1 to t sub I, for any interval, there will always be a rational number in here. So rational, and there will also always be an irrational number. So there will also always be an irrational number. Right, sorry, my writing is kind of sloppy there. But for any interval that we take within AB, so for any t sub I comma t sub I, there must be a rational number and there must be an irrational number. It doesn't matter how small the interval is. So we're saying that, like, the density of the rationals and irrational. So, like, even if I take, like, just to make a point very clear, 0.99 and 0.991, there's a rational number and an irrational number in here. That's the point, right? Okay, cool. It doesn't matter how small the interval is. All right. So what does this mean? That means that when we define our little m sub I, remember how we defined it? We said that little m sub I was the smallest y value attained in here. But wait, we just said that in here exists a rational number and an irrational number. And the y values that are put out by f of x are binary. It's either 0 or 1. And because we're guaranteed that there will be an irrational number in any interval and a rational number in any interval, it means that little m sub I is generically equal to 0 for any of these intervals. Okay, cool. And it also means that capital M sub I is generically equal to 1, regardless of what I is, right? Because, again, in any interval, we can find a rational and irrational number, and so we can just pick the y value there, and so we know that if it's irrational, it's 0, so that means that the smallest y value attained for the function in that interval has to be 0, and the biggest is 1, and so you get it. You get why these have to be true. But then wait, we said that u is equal to UFP is equal to, right? We said it's equal to the sum of the product of capital M sub I, which we just said is 1 for all i's. So that, and then times, what is it? It's ti minus 1. So basically what this is doing is, since capital M sub I is 1, it's just adding up the intervals. But if we add up the intervals, that's just a to b. So that's going to be, this is going to equal b minus a. Whereas on the other hand, L of fp, right? We said I equals 1 to n, of course. We said that this was equal to I equals 1 to n of little mi, but wait, we just said for this specific function, little mi is generically equal to 0. So 0 times, well, doesn't matter what I write now, ti minus 1, and so we see that this is going to be equal to 0, whereas this is going to be b minus a. Okay, so this is equal to 0, and this is equal to b minus a, which means that since UFP, right, is on any interval AB is just going to always be b minus a, nothing smaller, and L is always going to be 0 on the same interval, and of course here P refers to the same partition. We see that, like, if we take sup L is going to be 0, and inf u, so sup L is going to be 0, and inf u is going to be b minus 8. There's no way to reconcile these. There's no way for this specific function that the u is going to equal the L, and therefore there's no way that sup L is going to equal inf u, which means that this function right here is not integrable. It's an example of a function that's not integrable. Of course, you know, you could have a function that has even a jump discontinuity and it's still integrable. You can integrate it on here, and then you can integrate it on here and add up the two areas. So if you have, you know, finitely many discontinuities, that's not a problem. But if you're crazy like this function, well, that is a problem. Okay, I'm done. I hope you enjoyed this. I enjoyed it a lot.